population, and we have some sort of proportion of our population, like we want to know what proportion of Californians have a cell phone, or what proportion of Californians have traveled to Euro Disney, I don't know, some random proportion that we need to know. So in order to do this, we are given a sample, given p hat, a sample proportion, which is equal to x over n. So we're going to use that to create a confidence interval, and the formula for that is equal to p hat plus or minus z sub alpha over 2 square root of p hat times q hat all over n. Right? So this is the standard deviation guess, our assumption based on our sample. This is from the standard normal distribution. We got to figure out what is the z value that traps that little percentage that we want based on the confidence interval that they ask for. And then this is some p hat, right? The sample proportion, right? So this was 9.1. On the other hand, in 9.2, we are going to be taking values from a parent distribution, some population, parent distribution. It's got some mean, which we don't know, some sigma, which we don't know, but we are given some sample where we know n, we know x bar, and we know s. So either the word problem will specifically tell you these values, or you'll get enough information from like the raw data of a sample for you to figure out those things. And now this is when we know we have to use a t-distribution. So it'll be x bar equals to plus or minus t sub alpha over 2, s over the square root of n.
And you're going to, these are going to be at the end.
So the formulas in the back of your book, there's like a handout, like a fold out crib sheet thing. Those are the formulas I'll be giving you, and these are on there. So you don't have to memorize them, you just have to know when to use which applies where, and then how to interpret them, apply them in the right way. Good? Questions? Okay, so when we want to approximate a population proportion, here it is. It's a very simple little equation, but there's this whole crazy concept thing that comes behind it, right? And then here's this one. Again, when we want to approximate a population mean, then here's our formula. It's not that scary, but it's really difficult to really dig in and try and figure out where this formula came from and what it means. So that's hopefully what we've done.
You said the first one, approximate.
Population proportion. Good? All right, so moving on to the next section. So we were able to approximate proportions. We were able to approximate means. Now we're going to try and approximate sigmas, right? It's like the only thing missing that we haven't done. Let's come up with a way to create a confidence interval for the population standard deviation. Okay, so again, I'm going to start with the concept of what it is we're doing. It's not that you have to do all that writing on your own. And then we'll see the little formula that comes with it, and hopefully it'll be clear where that formula came from. Okay, so again, this isn't like a procedural thing, I'm just kind of giving you an idea of what's happening. So let's say that we have a distribution that's given. So let's say we have a normal distribution given. And let's say that that mean is 5 and a standard deviation of 3. I just made up those numbers, but let's say that that's the case. Okay, so then if we take a sample from here, let's say we take samples of size n equals to 7. Right? When we take one sample, then that one sample is going to have x bar, the sample mean. Let's just say that that sample mean was 6.2. And it's also going to have a sample standard deviation. Let's just say that sample standard deviation was 3.8. Right? Every one of these samples is going to have their own sample mean and their own sample standard deviation. So let's say we take another sample. 2. Let's say that that's x bar equals to 4.9 and s is equal to 2.7. And one more. About x bar equals to 8.2 and s equals to 3.3, and so on and so forth and so on and so forth. Okay, so the obvious choice is to think, well, let's just graph S's, right? We did that with means. Then we graphed the sample means and we saw that that was normal. Well, it turns out it's not that easy. It doesn't work is basically it. I mean, we can throw some fancy equations and show why it doesn't work, but it just doesn't work. Just graphing the S's on their own doesn't work. However, some brilliant person thought of this. They invented something called chi-squared. Now, chi-squared looks like this x, but it's got this wiggly thing next to it, so we call it chi. We write it as chi, and then we got a little square there. Now, the square is kind of part of the title. We're never going to try and square root it or anything. It's just kind of part of the title. Think of it as one single thing called chi-squared. And so chi-squared is the result of this little formula, n minus 1 times s squared over sigma squared. Again, there's absolutely no evidence as to where that came from or why it works or anything like that. That's like a really advanced idea in statistics, so if you want to move on and take the next stats class, that's definitely something you'll have to explore a little more. But for us, let's just explore what it means, okay? So what we're going to do is we're going to apply this little formula to each one of our values, each one of these values. So for example, to this first one here, we're going to find the chi-squared associated to this one, which would be, okay, n is 7. It's 7 minus 1 is 6. So it'll be 6 times the standard deviation of the sample, which is 3.8 squared, divided by 3 squared. Right? That would be the chi-squared of this particular result. Chi-squared. Chi-squared. Let's just figure out what it is.
Is it 6.2?
What's that?
Is it 6 or 6?
Oh, 6.2 is the sample mean. This 6 comes from the fact that it's n equals to 7. Therefore, the formula says just n minus 1. In fact, let me just scoop this all over. I'm squeezing it all in too much. I'll put this over here. Chi squared equals to n minus 1 times s squared over sigma squared. So for each one of these values in my samples, I want to find that. So it'll be chi squared equals to 7 times 3.8 squared divided by 3 squared. Right? This is 3.8 because the sample standard deviation is 3.8. And this is 3 down there because the population standard deviation is 3. And this is 7 minus 1, which is 6. This is 7 because n is 7 and it's 7 minus 1. Okay, so let me just find that value here. That's going to be 3.8 to the second power times 6 divided by 9. I get 9.6267. 9.6267. Okay, now let's find this chi-squared. This chi-squared will be 6 times 2.7 squared all over 3 squared, which will be 2.7 to the power of 2 times 6 divided by 9. We get 4.86. Last one. Chi-squared of this one is 6 times 3.3 squared all over 3 squared, which will be equal to 3.3 to the power of 2 times 6 divided by 9. So we get 7.26, and so on and so forth. So you keep doing that for all values that you withdraw, right? Every sample from that population has its own sample mean, its own sample standard deviation, and you apply this little formula to each of those. Okay? And now what we're going to do is we're going to graph each of these. So we take all of these results and we graph them. So, for example, 9.6267 is over there, and maybe over here we have 4.86, and then over here we have 7.26. Okay? So we keep going and we keep going and we find more and more and more results. And remember that the horizontal axis describes the possible answers. So this is all possible chi-square results. And the picture above is going to be the probability distribution. It tells us the likelihood that we would get such a result. And it turns out that these are going to look like this. It's going to have a picture that looks a little like this. We call that a chi-square distribution. Alright, so chi-square distributions are very different from the other distributions we've seen. So far we've seen a normal distribution and we've seen a t-distribution. Both of those were very, very similar. They were symmetric about the center. They both had that sort of bell shape. Here is one that looks nothing like a bell shape. It's got this weird wavy thing happening. It is not symmetric. It is not centered about 0. In fact, it starts at 0. This is 0 right there. Right, remember, the horizontal axis is all possible results from this formula. Can this formula ever give you an answer that's negative? Think about it. I'm taking some number and squaring it, another number and squaring it. Those two are never going to be negative. Is this ever going to give me a negative? N is the sample size. No, right? Even if the sample size was like 2, that'd still be 1. If the sample size, you can't have a negative sample size. So this is always a positive answer. That's why there are no values of chi-squared that are negative. Right? 0 forward. Got it? Got it? Got it? Okay, so it's got this wavy thing, so it's not symmetric, which means the smaller values are a lot more likely than these larger values. Good. And just like the t-distribution, the actual shape of chi-squared changes just a little bit based on n. So this, for example, is with n equal to 7, so the degrees of freedom equals to 6. Degrees of freedom equals to 6. On the other hand, if I had done this whole thing, but I had n equals to 8, the degrees of freedom would be 7, and the shape would be just a little bit different. Maybe the shape would be maybe something like that, like just a little bit different. Right? So they kind of vary just based on the sample size. There's a nice picture in your book regarding this, so we'll look at it now. Right? So they have slightly different shapes just based on the degrees of freedom, which is in turn connected to the sample size. So here's a nice graphic about that. So when n equals to 2, we get this ugly, weird blue thing. Then when n equals to 5, we get this one. When n equals to 10, we get this yellow one. When n equals to, when degrees of freedom equals to 15, we get this green one. When the degrees of freedom equals to 10, we get this yellow one. And when the degrees of freedom equals to 5, we get this one over here. Right? This is figure 18 on section 9.3. Good? Good? Okay, so this is a chi-square distribution with a particular degrees of freedom. And so when we do this process, we get this. All right. The geniosity comes in that this is something, these chi-square distributions are something that we call pivotal. Okay? Pivotal means that the distribution only depends on the sample size and not the population parameters of mu equals to 5 and sigma equals to 3. Meaning that if I did a whole different question, let's say I had a whole other normal distribution with mu equal to 8 and sigma equal to 4, but I still did samples of size 7, and I did this whole process all over again, well, I would still end up with the exact same chi-square distribution. Every population, no matter the parameters, as long as it's normal, so it's got to be a normal distribution, any normal distribution with any mean and any sigma, regardless of those, if they only have a sample size of 7, they're going to produce the exact same shape of this distribution. Okay? That's a big thing. And also, we have equations that help us find the areas underneath this curve. So that's, again, something outside the scope of this class. But I can go out to my bag of math tricks and figure out areas associated with these things. Okay, so we can go back to those, remember those crazy integrals we did in chapter 7 or I wrote down? We don't have to do that in here now. So for us, we have tables. Okay, some of your calculators will be able to figure these out because they have chi-squared functions in them, but I think most of your calculators do not. So this is a case where we are going to have to rely on our tables. Any questions so far? No? Maybe? Kind of? No? No? Maybe? Kind of? No? Okay. So.
Is there going to be questions about those those, things, the lines, colored lines?
Well, this is just to point out that they have slightly different shapes based on the degrees of freedom. But when you work on one problem, you're only dealing with one of them. And traditionally, we only write it in this kind of this curvy, smooth method here. So we can use all this to come up with a confidence interval. So let's tie that off and show you how that happens. So we have, traditionally we draw chi-square distributions this way. And we had degrees of freedom equal to, I think I said n was equal to 7, so say we have degrees of freedom equal to 6. And remember, we had lots of different values in there that were all the different chi-squared results that came from this little equation, n minus 1 times s squared over sigma squared. Okay? So now what we do is we come in here, and let's say we wanted to find a 90% confidence interval for sigma. Okay, so we have to go to this distribution. We have p of x there, and this is chi-squared, and we need to find the chi-squared values, the middle 90% of our data. 90%, right in the center, which means that each tail is going to have 5%. So I need to find this. Now, of course, we use very similar notation. Chi-squared, and then we say 0.05 to indicate that that's the chi-squared value that separates the lowest 95% of our data from the top 5% of our data. And this is chi-squared 0.95 to indicate that this is the chi-squared value that separates the lowest 5% from the top 95%. And now at this point, usually it's when we go to our calculator and do like inverse norm or inverse t or inverse chi-squared. Some of your calculators will have them, but most of them do not. So most people cannot use inverse chi-squared to find this value. We're going to have to go to our tables. Okay, so that's what our table looks like. Very limiting in the choices that we have for degrees of freedom up here. I'm sorry, not for both degrees of freedom as well as the areas. So we have to first of all look at the degrees of freedom we're working with, in this case 6, so that's this one, 6. And then we have to look at the area to the right. So we are looking for the one that has 5% to the right, that would be this one. 5% to the right, here it is. 12.592. So this guy is 12.592 with a chi-square distribution, 6 degrees of freedom. 12.592 is the number that separates the top 5% from the lowest 95%. This is not symmetric, so I can't just jump to the conclusion that's like negative 12 or something. We can't do that. There's no choice but to look it up and find out what this is. From our table, now we got to look at 95 and go down to 6 degrees of freedom. And I get 1.635. 1.635. Good. So between these two numbers, we will find 90% of our data. We're good?
So that's the only, I mean, this is the way we're going to do it.
Yes. For these, the table. Yeah. Okay. Unless you have it in your calculator, then you can use inverse chi-square to find it. But I think most of us do not. You have to have, I think the Nspire ones have it if you have an Nspire calculator. Well, I know for sure they do. Okay, so I like to label this as chi-squared left and chi-squared right, instead of these little decimal numbers. So I'm going to use this notation for a little bit, and hopefully it'll simplify things a little bit. So left, it's the one on the left, it's the smallest one, right? And then the right one, it's over here. Good? Okay, so what are those numbers? Those numbers are saying that 90% of my chi-squared values will land inside these two numbers, right? 90% of them will land in there. And what is the chi-squared number? It's a number determined by this equation. Okay? So for a given value, for a given sample, we will calculate our chi-squared, and our chi-squared might land in there. So from sample, oops, from sample, we have n minus 1 s squared over sigma squared is my chi-squared value, and hopefully it'll land in there. What are the chances it lands in there? There's a 90% chance it'll land in there, right? Under the, okay, so in order for me to calculate it though, I need to know n, I need to know the sample standard deviation, and I need to know sigma. Okay, but what this is saying is that, where did the other one go? Okay, so chi squared of 0.95 is less than or equal to chi squared of my sample, I'll put it like that, which is less than or equal to chi squared of 0.05, right? This is the chi squared of my sample once I calculate all that. And then I'm just going to use left and right notation. Chi squared left is less than or equal to the chi squared of my sample. And the chi squared of my sample is this equation. So I'm just going to write it as n minus 1 times s squared over sigma squared less than or equal to chi squared right. Is everyone with me so far? Right? The chi squared of my sample is this equation. This is chi squared left, which I got from my table, or I can use intervals, or I can use my calculator. This is chi squared right, which again I can get from the tables and all that. Okay? So in this particular case, I know that this number is 1.635, and this number is 12.592. But I'm going to leave it in general and solve it in general, and then we'll go back and plug it in for these particular numbers. Okay, so I don't have this. I was given this result. I was given S. I was given N. I can figure this out from my table, but this is the thing I don't know. So what I want is to come up with a triple inequality that traps the sigma in the middle of it by itself. Yeah.
Where were you given the S?
It's a part of the sample, right? For all these questions, we're trying to come up with a confidence interval for sigma from a sample that will be given to you, and the sample, you can get the sample standard deviation. Okay, so we want to solve for sigma squared. So the first thing I'm going to do is I'm going to multiply all three parts of my inequality by 1 over this amount. Okay, so I'm going to multiply this by 1 over n minus 1 s squared, and then multiply this by 1 over n minus 1 s squared, and multiply this by 1 over n minus 1 s squared. That'll cancel these guys there, and so I'll be left with the following. It'll be chi squared left of n minus 1 s squared is less than or equal to 1 over sigma squared, which is less than or equal to chi squared right of n minus 1 times s squared. We're good so far?
No.
What's wrong? Say everything.
Okay, I think
All I did is I multiplied everything by the reciprocal of this so that the numerator there cancels. My goal is to get this thing by itself. So I canceled the numerators. I got to do it to all three parts. I got to make sure that when you multiply or divide by a negative number, you got to change the direction of the inequality. However, I know s squared is positive. I know n minus 1 is positive. That doesn't cause any problems. The inequalities stay facing in the same direction. Okay. Now I'm going to flip all of these. I'm going to multiply by the reciprocals. So I'm going to rewrite this as sigma squared over 1. And I'll rewrite this as n minus 1 s squared over chi squared right. I'm going to flip this one and write n minus 1 s squared over chi squared left. And when you multiply by the reciprocals, when you flip all the fractions that way, what happens? We got to change the direction of the inequalities. Okay? Why is that? Separate little example. Think about this. 1/2 is definitely smaller than 5 over 6. Yes? Is that true? 1/2 is definitely smaller than 5 over 6. But now if you just flip them, we end up with 2 over 1, and then here we get 6 over 5. So this is definitely smaller than that one. Sorry. 1/2 is definitely smaller than 5/6. Right, this is a little bit less than 1. This is a half, so this is definitely bigger. But now if we just flip them, then we end up with 2 over 1. and then this is 6 over 5, and this is just a little bit more than 1. This is like 1.2, whereas this is 2. That's definitely bigger. So we got to change the direction of the inequalities whenever we flip the fraction like that. Right? A little throwback from algebra days. Okay, so now that we have that, now we have the standard deviation squared right in the middle. That's sort of what we wanted, except we wanted just sigma, not sigma squared, so we take the square root of everything. Take the square root of this guy, and take the square root of that guy, take the square root of that guy. And the other thing I'm going to do is that we have the biggest answer there now, and the smallest one there, and we're used to seeing it in the other direction. So all I'm going to do is I'm going to put this first, then the middle, and then I'll put this last. Okay? So we will end up with n minus 1 s squared all over chi squared right is less than or equal to sigma less than or equal to n minus 1 s squared all over chi squared left, and we got to take the square root of each of those. Okay, so it's kind of squished there, so I'm just going to copy that up here. N minus 1 s squared all over chi squared right, square root of it, less than sigma, less than n minus 1 s squared all over chi squared left, take the square root of that. Yeah, questions?
Is this still a concept or is this?
Yes. Well, this is the formula now. So this is the actual formula you'll be given, and I'm just trying to describe where it comes from. So a very important thing that confuses people a lot, notice that over here when we were looking at the chi-square distribution, we found chi squared L, the left one, the lower bound there, and the right one there. So this is the smaller number, this is the bigger number on the left and the right. But then when our final answer comes, they get kind of switched. Chi squared right is actually on the left, and chi squared left is actually on the right. And that's because when we did this flipping thing of the fractions through our algebra skills, we see that it changes the direction of the inequalities, and therefore it flips their location. Okay, so don't let that confuse you. So this is the biggest chi-squared value, goes over here. It's the right one from our distribution, and this is the smallest of the chi-squared values. The one on the left goes on the right of our interval.
So are you saying that we're not going to get an exact answer for, like just between the two of them? Or we're not going to get an exact answer?
What do you mean it's between the two of them? We're getting an interval, yeah. This whole thing is about creating a confidence interval, right? So this is going to be creating a 90% confidence interval, right? Because we started with 90% there. We found those two chi-squared values, and so we see that this would land somewhere in there with a 90% likelihood. And now we just manipulated this whole equation to trap the sigma in the middle and have a little formula for the bottom and the top part that traps the middle sigma. So we have an interval for sigma. Right? So we know everything from there, and we know everything from there, and we can find that confidence interval.